This is the fourth experiment, and in this experiment you're going to prepare the borane amine adduct, which contains BH3 on one side, the Lewis acid side, and tertiary butylamine on the Lewis base side. Now, before we start with the adduct, we have to look into the interesting borohydrides, which are used extensively in organic synthesis: B2H6, B4H10, B5H9, B10H10 2 minus, B12H12 2 minus, and so many hydrides, and they have curious structure, as we will see later. Now, diborane, which is B2H6, this is the BH3 dimerized, and it can be prepared by using the sodium borohydride with BF3 to form B2H6 and NAB4. This is the structure of the B2H6, and it shows the two molecular orbitals formed. The two molecular orbitals formed by the pz orbitals of the boron and the s orbitals of the hydrogen. As you know, the pz from the boron on the right side and on the left side and the s orbitals are summed up into one molecular orbital, and the boron on the right side and on the left side, they form another molecular orbital with the s orbitals by subtracting the px orbitals. So we end up with two molecular orbitals forming the four bonds, and this is the structure of B2H6. Now the two bridging hydrogen atoms lie above and below the plane which contains the boron atoms. Each terminal hydrogen atom bonds to one boron atom, so each of the bridging hydrogen atom bonds equally are bound to two boron atoms. So in diborane there are 8 BH bonds, which we expect to have 16 valence electrons, and in fact this compound contains only 12 valence electrons to form the 8 bonds, 3 from each boron atom and 1 from each hydrogen, and they are holding the molecule together. B2H6 is the stable form dimer of BH3. It will dissociate easily into two BH3s, which we are going to use in this experiment. Now this reaction between BH3, which is the Lewis acid in the form of B2H6, and the Lewis base in the form of tertiary butylamine. Now the tertiary butylamine with the lone pair on the nitrogen will interact with the empty orbital in the Lewis acid BH3 to form a sigma bond and a sigma star bond. The two electrons go in the sigma orbital, and we form the adduct BH3 NR3. Here in this reaction, to facilitate the reaction, we mix NaBH4, sodium borohydride, with the salt which we are going to prepare in this experiment, which is the butyl ammonium chloride salt. And when we mix the tributyl ammonium salt with NaBH4, we're going to end up with the adduct BH3 and R3, And this experiment, you have to take care about the toxicity of B2H6 and to make sure that it doesn't, the fumes go in the lab. Now, the first part, we are going to prepare the this is the first part of the procedure, which you're going to prepare the tertiary butyl ammonium chloride salt, and you mix HCl with the tertiary butyl amine to end up with the white solid salt with a melting point 96 degrees centigrade, and you run the IR of this salt. This salt forms by the tertiary butyl ammonium on one side, positive, and the chloride on the other side. And we're going to use this salt to prepare our adduct. When we mix the tertiary butyl ammonium with NaBH4, as you see in the equation here, you form the adduct plus NaCl plus hydrogen will be liberated. Now, the adduct has some interesting properties. It reacts with HCl, it reacts with HF, and more interesting, in this slide, it reacts with the alkenes to liberate BCH2, CH2R3, and the amine. And we're going to proceed with heating the adduct in the oven at 100 centigrade. It will form the cyclic B3N3 ring, and if you heat it to 200 degrees, it will form the cyclic compound B3N3 with conjugated pi bonds, like what happens in the aromatic carbon compounds. Experimental procedure, we have an alternative procedure to prepare the tertiary butyl ammonium chloride salt, which is in the synthesis of tertiary butyl ammonium salt. You dry the flask, then you add tertiary butyl amine. In the dry flask, you use a stopper, but very loose stopper. Then you add ether as a solvent. Then you prepare glacial acetic acid on the other side in a different flask. Then you mix the solutions to form the tertiary butyl ammonium salt, and you filter it off as a white solid. Now, reaction to produce the adduct, you prepare a 3-neck round bottom flask with a magnetic stirrer, and you start by adding on the left side the calcium chloride tube with a cotton plug to keep the solution mixture or the reaction mixture dry with time. Then you add your salt and the NaBH4, and you stir for certain amount of time. Of course, the solvent is dry THF. You make sure the THF is very dry, otherwise the reaction will not proceed. Now, after the reaction proceeds for a while, you stop the reaction and you filter the excess NaCl and the junk. Then you move rotary evaporator, the solution, after you filter off the excess thing not wanted. You take your solvent THF to the rotary evaporator to take the THF out of the solution, and you end up with the adduct. Now, if you're not familiar with the rotary evaporator, it's a condenser rotating with the and with a vacuum pump, and you put your solution on the condenser, and it keeps rotating electrically, and the vacuum takes the pressure from inside, and the THF evaporates and goes into the receiving flask, and it rotates to stop the bubbling of the solution. After this process, you end up with the BH3 and CH33 adduct, and you characterize this product by calculating the percentage yield. You weigh the flask before, then you weigh it after, so it gives you how much product you get, and the melting points if it's not liquid, and the infrared spectrum, and you know the BH and the BN bonds, most important, and you solve the problems here before you come into the lab.